share the video.
Go ahead. It's live.
Okay, so welcome to this session from the main track of LADC. We will start the session with the work on the performance of using parallel state machine replication to implement blockchains. We will play the video, and after that, we will have some time for questions. So, Mateus, if you can play the video, please.
Hi, my name is Aldenio Burgos, and I'm a master's student at the Department of Computer Science at the University of Brasilia. I came to introduce you today to the paper on the performance of using parallel state machine replication to implement blockchains. Wrote this paper together with the Professor Eduardo Alchieri and the Professor Fernando Dott. My presentation has 5 sections. I will start with an introduction and some preliminary definitions. Then I will talk about the application we created. And finally, I will explain the experiments and our conclusions. State-machine replication is a traditional approach to implement fault-tolerant systems. It's a simple and effective approach. Nowadays, it is used in many relevant systems like Azure and Bookkeeper, etc. State-machine replication creates for the clients an illusion of a single highly available server while coordinating interactions between clients and a set of server replicas. In order to get there, all the replicas must start from the same initial state, execute the same set of commands in the same order, and reach the same final states. To maintain these properties, several protocols are used, such as reconfiguration, recovery, and atomic diffusion. In addition to these protocols, commands need to be deterministically and sequentially executed in the same order across all replicas. The blockchain buzzword has been used to name distinct concepts, sometimes as a data structure, sometimes as a system model. When describing a data structure, the blockchain describes something like this. Generally, you have a chain of data blocks where each block points to the previous one through a hash pointer, which is a structure like this. Usually, it has the previous block address and the hash of all its contents. When referring to a system model, blockchain usually describes a distributed peer-to-peer system that uses a consensus protocol to evolve a blockchain data structure in a consistent way. Although the two have the same common goal, which is to keep state replicated and consistent across the various replicas, state-machine replication blockchains also have differences such as the handling of executed requests log and the network reconfiguration model. However, in spite of these differences, we have several works in the literature that involve combination of state-machine replication and blockchains. In 2020, the article by Bassani et al. Studied on the use of a classical Byzantine fault-tolerant SMR as a building block for a blockchain. Among other conclusions, a considerable limitation in the performance of the blockchain was detected, given the need for sequential execution of costly cryptographic operations very common in this type of systems. This performance issue of classic state-machine replication related to its sequential execution is of our knowledge for a long time. The studies on parallel state machine replication have emerged because of this problem. In general, the basic idea of parallel SMR is to coordinate a set of threads in all the replicas to execute in parallel the requests that do not conflict and sequentially the requests that conflict with each other. We say that two requests are conflicting or dependent when they access at least one variable in common and at least one of them modifies that shared variable. However, we say that two requests are non-conflicting or independent when they access different variables or just read the value of shared variables. Dependent requests demand coordination between threads so that they are executed sequentially in the same order in all replicas. Independent requests can be executed in any order, including in parallel, without any loss of consistency in the system. In our tests, we used parallel state machine replication with hybrid scheduling. And now I'm going to show you how it works. The whole diagram I will show in this slide represents the internal scheduling structure of one HSMR replica. Here in the bottom is the legend of the diagram. As in a classic SMR, requests are sorted and delivered in the same total order across all replicas. When the requests arrive, they stay in this queue, waiting for the schedule to be executed. Using the hybrid scheduling approach, each request delivered has a label defined by the client, and it tells the server which partitions or shards that each request will access. Shard 1, shard 2, shard 1 and 2. This label is read by the classifier thread. The classifier is a special and unique thread in each replica. It reads the request labels and places them in the correct partitions. Each partition or shard has its own input queue, a parallelizing thread, a partition of the request's dependency graph, partition 1, partition 2. This is conflict ordered set. This is the kind of graph we are using. And a set of execution threads. Each parallelizer reads requests from its input queue and populates its partition of the dependency graph, placing requests as nodes and dependencies as edges. In this diagram now, we can see the hybrid scheduling of a running replica. As the requests are inserted in the graph, the execution threads get the dependency-free requests to execute and then remove them from the graph. This process will release other requests for execution and so on. The application created for our experiments was named ParallelCoin. It is a client-server system for a multiple digital currency. Each currency operates on a different application partition of ParallelCoin. ParallelCoin was based on the Bitcoin UTXO model from Nakamoto 2008, but each token in ParallelCoin represents a value in a specific currency owned by some user. Users are represented by their public keys, just as Bitcoin, and all requests are signed by the client's private key, just as Bitcoin. The operations that parallel coin has are issue, which creates new token in a currency, transfer, which transfer tokens between users without changing the currency and without touching more than one partition. It only touched one partition. Exchange, which transfer tokens between users and changing the currency. Exchange operations will touch more than one partition. And balance, which is a query, read-only operation, and returns the sender's token balance in the requested currencies. The balance operation can access one or more than one partitions. In our experiment, the knowledge of application semantics that is provided to the HSMR is a function based on these two rules. This way, the parallelizer is able to identify whether or not a new transaction is dependent on each transaction that is already in its dependence graph partition. First rule is if two operations are both balance operations, they never conflict. Rule 2, two operations conflict if they share at least one user and a partition, and they are not both balances. Our experiments were conducted on EmuLab. We used the 8 machines connected to a 10 gigabit switched network. We used the BFT Smart as our base SMR implementation. We configured it to tolerate Byzantine faults. We used 4 servers as replicas, and we used the other 4 machines to distribute evenly 2400 client threads. In our test series, we preloaded all 2400 users, each one with 10 tokens of value 1 in each currency. The exchange rate of 1 was settled to all currencies, and after each write operation or transfer or exchange, the initial system state is restored. These are the algorithms we choose for hashing and digital signatures. And now we can see the results of our experiments. These graphs here show the throughput in thousands of operations per second for the parallel coin with the sequential SMR, is the white box, and the HSMR configured with different numbers of shards and different numbers of executor threads per shard. In charts A and B, we present the results of a workload with 90% of balances and 10% of transfers. In the first chart, all operations access only a single partition. In the second chart, 5% of all operations accesses 2 partitions at the same time, or 5% of balances and 5% of transfers were exchanged. 5% of balances asks for more than one partition. In chart C, we have the same view, but here the workload is 95% of transfers and 5% of exchanges. There are no query commands, no balance commands here. They are all write commands. Observe the performance of parallel coin with the classical SMR is this, and this, and the performance gain with HSMR as more partitions are added and more threads are dedicated to each partition. Our conclusions. Through a digital currency application, a recent work, Sunny et al. 2020 demonstrated that the use of traditional SMR as a building block affects and more threads are dedicated to each partition. Our conclusions. Through a digital currency application, a recent work, Sunny et al. 2020, demonstrated that the use of traditional SMR as a building block affects the performance of blockchain applications. This study we are presenting now also uses a digital currency application called Parallel Coin to demonstrate that parallel SMR can minimize the performance limitations previously identified as they allow a portion of the transactions to be executed in parallel in the replicas. Experiments carried out with our implementations show that parallel coin with HSMR has a performance up to 7 to 22 times that of the classical solution. That's all I was going to present to you, and now we are waiting for questions. Thank you.
All right, so thank you, Aldenio, for the presentation. We have time for a few questions, so anyone from the audience would like to ask some question to Aldenio?
Yeah, I have a question if nobody has. So thank you, Aldenio, for your presentation. Very interesting work. Just a curiosity, I've seen that you have, if I understood correctly, you have a classifier that decides if the request can be done in parallel or not, right? So how does this classifier works? What does it look for? How is this decision made? If you can comment a bit on that.
Aldenio, your microphone is muted, so we can't hear you yet.
Can you hear me now?
Yeah, no,
Okay,
that's
okay.
perfect.
Sorry. The classifier you asked, right? So the
Yes.
classifier reads the labels in the requests, in the commands, and puts the command in the queue. If the command is labeled to run in the partition 1, it just puts in the queue of partition 1. If the label of the command says that the command is going to run or to touch in state of partition 1 and 2, the classifier puts it in the both queues. That's the classifier is very simple code. The decision is made in the client side of the system.
Okay, thank you. I understand. So yeah, requests already come with this label that say where they are going to be executed. Yeah.
Yeah.
Thank you.
Yeah, just complementing the Leonardo's question, could you give me an example with the operations you implemented in the blockchain? For example, could you illustrate which attribute or which information of the command can be used to the classifier distinguish which queue it will be dispatched?
Yeah, it's very simple. In our sample, we used the currency as a partition of the system. So our coin application or digital coin application, it works for many currencies like dollar, real, and other currencies, peso. And when the user sends a transfer from two Brazilians in real, from real to real, so it only touches the partition of real, the partition number 1. And if the client will label it, it only touch the partition number 1, and the classifier will put it in the real transfer queue, the partition number 1 transfer queue, right? And if the command is a transfer among two Americans in dollar, in United States dollar, so the partition will be the partition number 3 or 4. So the client will know which is the number of the partition for dollar, and will label it. This request only touch the dollar partition. So the classifier will put in the dollar queue. If you have an exchange, if you are sending dollar reais for Canadian dollars, you are doing exchange. It will touch both partitions, and the user will label it with both numbers and the codes, and the classifier will put it in both queues. It's very, very simple.
Oh, perfect. So, is there any other questions from the audience? You can just open your microphone and ask it directly, or you can write in the chat. In the meanwhile, I will ask one question. So we could see in the results that the dependencies might hurt performance. So actually, depending on the kind of dependence, they can involve more partitions, and that has an effect in performance. In blockchain systems, usually we have one entity that produces the blocks and then issue the blocks to be proposed and eventually make part of the chain of blocks. Is there a way to avoid or minimize the dependencies when this entity is preparing the block? I mean, is it possible or is it interesting to choose wisely which transactions would be in the block before sending them to the system? Is there something in this direction, or that's not important actually?
In public blockchains that we usually speak about like Ethereum and Bitcoin, they are the most famous blockchains. The miner, which is the node that builds the block and sends it to the network to approval to be included in the blockchain, in the chain of blocks. They have a pool, main pool, a pool of requests, pending requests, and they can choose any way they want the list of requests that they are going to select for block mining to be part of the block. So they have an algorithm that don't let them choose conflicting commands to put in the same block, because if they do this, they will spend money, energy trying to mine a block that will be rejected by the network. So they do not use this. They do not choose conflicting requests, but you have private blockchains that use other kinds of algorithms for instead of mining that are faster, and they can use some kind of some kind of selection which is faster, and they can choose how to they can choose non-conflicting requests too. If they choose conflicting requests, they will have problems. Okay.
Okay, thank you. Is there any other question for Aldenio? I will ask another one, Aldenio. Very quick question, I think. It's more curiosity. Are there benchmarks or data sets similar to the blockchain application you modeled? I asked that because we saw a micro benchmarking that you can change the percentage of conflicting and kinds of operations, but is there some realistic observation or tool that show us that kind of workload?
No, we don't know. We don't know the benchmarks for blockchain. They are not known, not that we know about it. And we had to choose our own benchmarks because we don't have a industry, the full industry benchmark that are known.
All right, thank you. So thank you again. We don't have applauses from the audience, but feel congratulated by the audience for your work. And I think we can move on. If you have, in case you have questions to Aldenio, you can just write in the chat, and he can interact by there. So thank you, Aldenio. And now we can move to the next presentation. So the paper is characterizing and injecting faults in executable models specified with FUML. Authors are Guilherme Wilson dos Santos Lopes and Leonardo Montecchi. Leonardo will be the presenter. So we can play the video now, and later we have some minutes for questions.
Welcome to the presentation of the paper characterizing and injecting faults in executable models specified with FUML. My name is Leonardo Montecchi from the University of Campinas in Brazil, and this is a joint work with Guilherme Wilson dos Santos Lopes, also from the University of Campinas. The context of this paper is in fault injection, which is an established approach to evaluate the dependability of systems, and executable models, which are basically restrictions to UML models, UML diagrams, to enable their execution. In this paper, we investigate the application of fault injection to executable models specified with FUML. We understand, characterize the kinds of faults that can be injected in these models, and then we realize an injection mechanism based on model transformation, and finally we apply the proposed methodology to a simple example in the space domain. Just a little background. Fault injection is defined as the deliberate introduction of faults in a system to evaluate their impact. And it is typically used to understand if fault tolerance mechanisms work as expected, and to evaluate them in the system. Fault injection may be applied at different levels. In the past, it has been applied at physical level, which means, for example, applying radiation or interference. At hardware level, which may mean to short circuit pins of hardware components. At software with software implemented fault injection, and also on models. For example, Modify is a well-known technique for doing fault injection on Simulink models. The idea of applying fault injection on models is that, as everything now related to models, that it allows discovering problems early, so discovering faults in the specification, problems in the specification early in the development of the system. Executable models can be seen as a part of model-driven engineering, or at least related to model-driven engineering. Model-driven engineering is a software development approach which is centered around modeling and the generation of artifacts from this modeling, and in particular then we talk about structured and machine-readable models that can be processed automatically by computers. And in this context, we talk about execution of UML models. There have been several approaches in the past, or multiple approaches in the past, since a long time. For example, UML-P by RAMP, or executable UML, which is XUML, or now XTUML. And the idea is that also if you execute specification models, you are able to discover faults in the specification earlier and discover faults that maybe cannot be discovered with formal techniques, with, for example, model checking, and also discover faults that can may be connected with data, and also you are able to simulate the model jointly with data. However, there has been incompatible approaches, no? So there have been multiple approaches for model execution in the past, but with some differences between them, and therefore it has been introduced a standard which is called foundational UML. So it is a standard for the execution of a subset of UML, which has been defined, released by the Object Management Group, or OMG, with the objective to provide a standardized way to execute formally a part of UML. So this standard is called Semantics of a Foundational Subset for Executable UML models, or Foundational UML, or FUML. It was first introduced in 2011, and then latest version is from this year, from June this year, 2021, and it is version 1.5. And here you can find the specification. Basically, it is a restriction of class diagrams and activity diagrams, so to enable a precise execution of models. So just a quick overview on main elements which are included in FUML. So FUML, as I said, is based on class diagrams and activity diagrams. The main executable element are activities. So when you execute a FUML model, you execute an activity. Activities are composed of actions, with each action representing another behavior. So each action is actually a reference to a method call or to another activity. And actions are connected by control flow elements, so edges, control flow edges, which determine the sequence of these actions, so who comes before and who comes later. And object flow, which determines the flow of information between actions, so how basically input and output parameters flow through these actions, and more specifically through input pins and output pins, which are owned by the action. So these are the main elements. As I said, there are restrictions with respect to what can be done, what can be specified in the complete set of UML models. There is some tool support available, in particular Mocha, which is a plugin of Eclipse Papyrus. So Papyrus permits creating UML models, and so also models which are compliant with FUML, and Mocha, if the model is compliant with FUML, is able to execute it. Here there is an example of an FUML model, an activity in which two values x and y are summed, so the sum of two values x and y. And we can see the main elements. So we have an activity, which is this diagram, then we have the action, the control flow, the pins, and the object flow, just to have an idea of how an FUML model is organized. And in the simulator, in Mocha, you can see the execution of the diagram with green elements being the parts that are being executed. And so here you can see, if you were running, doing the execution, you could see which part of the model are executed. So in this paper, we defined the methodology to inject faults in these models specified with FUML, with the idea to allow the analysis of exceptional behavior on FUML models and not just the nominal behavior. So this is an overview of the approach we proposed. So we have a first step in which we define the system model and the FUML model based on class diagram and activity diagrams. Then in a second step, we analyzed the fault injection literature and extracted which are the possible faults that can be introduced in this kind of models. And from this specification, then we can add fault specification in the system model. Then with a model transformation step, takes as input the system model and the specification of faults and generates a modified model, a model with faults being injected. And finally, we execute the model with comparing potentially with a nominal execution, so to see if what is the impact of this fault on the system, and so to see if the system works as expected or not. And here there are some tools that we used in this methodology. So everything inside the Eclipse modeling framework. We use, as I mentioned, Papyrus as diagram editor here. We use Viatra and Extend for the model transformation here, and Mocha for the execution engine here in the execution part. Okay, so the first step was to analyze the faults that can be injected in FUML models. So we starting from work already existing in the literature on software faults, so faults at software level, we tried to understand how these faults were mapped to FUML models, so which were the corresponding faults, modification in the model corresponding to these software faults, and in particular we based on the work of Durais et al. In 2006 and Natella et al. 2013, from which we used the taxonomy of faults. Then we, after understanding which are the faults, we defined a way to specify these faults on FUML models, in particular with UML comments. So faults to be injected are specified with UML comments that define the kind of fault, the location, and parameters of the fault. And we do this with an ad hoc language. So we define a simple language that is used inside UML comments to do the specification of faults. So describing the kind of faults, the location, etc., etc. And then we define the injection procedures, so how the fault can be actually injected, so the steps that should be realized to actually do the injection in the model. So we, for each of the identified faults, we defined the steps. You see here, these two are in English because are in the paper. These others are in Portuguese, are in a technical report of ours. But we have this for all the identified faults. And then, based on these steps here, we did the implementation. So we implemented the injector based on model transformation. So the injector takes as input a FUML model with the annotations of faults on UML comments. And then as output, we produce a modified FUML models which contains the fault or faults injected. The implementation has been done with Viatra and Extend, where Viatra identifies the faults and the patterns, and Extend is used to actually do the transformation. So for each fault, we have a kind of procedure pattern in Viatra and Extend that is used to actually realize the injection. Then the last contribution of this paper is to apply the proposed approach on an example application. So we did not complete an extensive case study, but we exercised kind of a proof of concept on some example models which are based on a real application in the space domain, and in particular the satellite Nanosat CBR2, which is a nanosatellite developed by INPE, the National Institute of Space Research of Brazil. In this link you can find more information on the system. Basically, it is a nanosatellite of the CubeSat family with two units, and it is composed of an onboard computer and some scientific payloads which are actually providing the functionality of the system. We based our work on existing public documents to do the modeling. So we did not have FUML models of the system. We created them based on public documents, and references are in the paper if you are interested. And in particular, we focused on the Langmuir probe, which is a scientific payload which analyzes, gathers data from the atmosphere and the space around it. A payload related to physics experiment, which basically is gathering data and transmitting it to the onboard computer. So we modeled its behavior with FUML, we injected faults and simulated its execution to see if we could find some problems or the effects of these faults. So we have some models like this of the system. Then we did some injection like this. In this case, we injected the fault in this connection here, in this object flow here. And among the results, we could find that after the injection of some faults, and in particular this one, we could identify a potential loop problem, a potential problem of infinite loop in the system, which could be solved by adding a timeout. So we can see that without this countermeasure and the timeout countermeasure, the injection of fault can have different consequences, and so we get a kind of confidence on the applicability of our approach, even if it's a small example for the moment. So in this paper was a first attempt at applying fault injection on FUML models. We defined this methodology for defining faults and defining the injectors, etc. And we did this example application, which in our opinion revealed the feasibility of the approach, but further evaluation and further development is needed. As a future work, we plan to improve the specification of faults, so maybe with a graphical interface or something more user-friendly instead of just UML comments. We plan to work on revising and extend the classification of faults, and also, of course, mainly now to evaluate the approach with a more extensive case study, potentially in the next satellite of INPE or other projects or with other partners. But one of the challenges in doing this is that the adoption of FUML is actually still limited for what we could see. And so this is one limitation of potential further evaluation. So we would need to find developers and people who are experienced in FUML and that are using it in their projects, which may be not so straightforward. Okay, so this was our paper. Thank you for your attention, and please, if you have some questions or doubts, I will be happy to answer them and to discuss the paper in the session. Thank you.
So, well done. Thank you, Leonardo, for the talk. Do you have questions from the audience to Leonardo? Remember, you can just turn on your microphone and ask directly, or you can write in the chat if you prefer. Well, in the meanwhile, I will ask you one question. So, you mentioned in the proposed methodology a model transformation, right? So this is one of the steps. I wondered if the generated model can be used as an input to other tools as well. For example, a model checking tool. So we could model a FUML system, and you could simulate its execution or analyze it to model checker, for example. Is it possible? How do you see this reuse of the model itself to other purposes?
Thank you for the question, Rico. Yes, I mean, these models are, all this work that we have done is inside the Eclipse modeling framework, which is also provides a standard for representation of models. So these models can be used, both the source model and then the one produced by transformation can be used by any tool that is compatible with the Eclipse modeling framework. So yes, it would be it would be interesting, and so maybe they can be used directly, or maybe you can have other transformations that maybe generate the input for some model checking tools like, I don't know, Upal or others. And yes, it would be complementary, because you can on one side check with formal properties, and on the other side simulate with maybe data, real data, and things like that. Yeah.
Okay, very nice. Is there any questions from the audience? Just remind you, you can write in the chat and I read to Leonardo, or you can ask directly. I will ask him another question, so Leonardo. Supposing someone wants to define new fault behaviors and extend your tool with the new classes of faults, which steps would be necessary? Is it possible? It's allowed to, or actually, it's simple to extend the tool to incorporate new failure models?
Yes, it is possible. Basically, you will need two steps that will be needed. The first is to define how this fault is specified, because we as I mentioned, we created this simple language to do the specification of faults to be injected in the model. So we need to extend or adapt this language to be able to specify these new faults, and then the transformation. But basically, the transformation is simple because for each fault there is kind of a procedure that does the injection of that fault. So it's kind of modular, and so you can just add a new procedure for this new fault, and this would be the extension. Yeah, and I did not mention, because the code is still maybe not perfect, but we have a GitHub repository also. So maybe if someone is interested, maybe we can you can send me an email or get in contact. But yeah, we have a GitHub. I've not mentioned it because we are still organizing it to have it more accessible for external people.
Yeah, that's interesting. I not use it with the Eclipse plugin you mentioned, so that's the reason I asked about the model transformation, which kind of output it produces, because there are some standards, right? So label transaction systems that you can use in other tools, and also I asked about the modeling of new behaviors. Because I was not understanding actually how the procedure would be implemented, if how is the effort in terms of coding. But I will take a look in the GitHub. I think it's really interesting work. So is there other questions from the audience? I think it's not. You just mentioned that as future work, you intend to investigate other classes of faults. I don't know if you had already checked about that as a literature, but do you have an idea what is missing, or what the team wants to improve in this field? And also, just extending the question a little bit, do you see some kinds of faults that would be more challenging to model? For example, some behaviors that would be transient or non-predictable, or something like that?
Yeah, thank you for the question again. It's very interesting question. So I mentioned to extend the fault model for different reasons. First one is that we based on some work that I mentioned, in which they made a list of which are the most most common fault in software. So we took this list as a first reference, but actually this list of most common faults come from a bigger list of software faults. So we would like to go through all of them and see how this can be applied to FUML models. And the other point is related also to the second part of your question. So there are some faults which are more challenging in the sense that sometimes the model that is generated may not be executable or may not be correct, because for example, a fault can be to remove some or change some connection, but maybe in some situations you remove a connection, but you don't have another one to substitute it, because it depends on the types of data, and so you have some situations in which you may find where to inject the fault, but you may not be able to generate a correct model. So this is something that we want to analyze better. Yeah.
All right, thank you. If there are any other questions to Leonardo, I would ask you to write it in the chat, and I believe Leonardo can answer or interact by the chat. So once again, thank you, Leonardo, and congratulations on your work. So we should move to the next presentation now.
Thank you.
But before starting the next work, let me just confirm with Sahid, because we tried to connect it with him before, and he was unable to turn on his microphone. So Sahid, could you solve this issue or not?
Yeah, can you hear me now?
Yes, perfect. All right.
Okay, good.
Yes. So let's move on. The last presentation on this section is the work entitled Modeling and Analysis of Fire Sprinklers by Verifying Dynamic Fault Trees from Sahid Khan, Just Peter Katoin, Matthias Volke, Ahmed Zafar, and Falak Sher. So we will play the video now, and later we have some minutes for questions.
Hello and welcome to this presentation. My name is Shahid Khan. I am a PhD student at RWTH Aachen University, Germany. The title of my presentation is Modeling and Analysis of Fire Sprinklers by Verifying Dynamic Fault Trees. Here is the outline of my presentation. I will start with a brief introduction of the topic. Then I will discuss the case study we have used for our experiments. Afterwards, I will show some of the identified scenarios that we think are better modeled using dynamic fault trees. Then I will discuss some experimental results and conclude my presentation with some pointers to future work. Let's begin with the introduction. This work is related to fault tree-based analysis of systems. Fault trees are logical diagrams that are used to model the situations such that how Boolean combinations of failure modes lead to the occurrence of the top level event. Fault trees have two types of elements: basic events that represent the failure modes of systems, and gates. There are two types of gates: AND gates and OR gates. This fault tree is modeled for a top level event that shows the failure of fire protection system, and this can happen if either fire detection system fails or fire suppression system, that in this case is the water deluge system, fails. Fault trees are highly intuitive to model. They can be analyzed using binary decision diagrams, simulation-based methods, and analytical methods, but they lack expressive power. That is, static fault trees cannot model temporal interdependencies of failure modes. Dynamic fault trees were proposed to mitigate this expressive power limitation of static fault trees, and dynamic fault trees extend SFTs by many dynamic elements. For example, dynamic fault trees have a standby type basic event that can capture the failure rate of a component in its active and passive mode. Then DFTs also have probabilistic dependency gates that can model common cause failures, probabilistic priority AND gates that fail if the inputs have failed in a strict left to right order, spare gates that model the spare management of systems. Dynamic fault trees have involved semantics, however, they have high expressive power, and most of the scenarios encountered during modeling of engineering systems can be faithfully captured using dynamic fault trees. The analysis of dynamic fault trees is performed using simulation-based methods and analytical methods. In this work, we are interested in probabilistic model checking, which is an analytical method. Let's look at the workflow of probabilistic model checking. Probabilistic model checking starts with a reliability model in an appropriate language, for example, a static fault tree or dynamic fault tree. And then we construct the underlying probabilistic model of this reliability model and feed this model to probabilistic model checker along with the measure of interest. In our case, the measure of interest is reliability, and we encode our measure of interest in continuous stochastic logic. Probabilistic model checker gives us a numerical value that corresponds to this measure of interest. We are using a Storm probabilistic model checker, and let's quickly look at why are we using Storm model checker. This is the performance graph from QComp computation that was held in 2019, and this graph shows that Storm model checker outperforms its contemporary probabilistic model checkers, including Prism, both in terms of computation power, it solves the instances much faster as compared to other model checkers, and also it can solve more instances as compared to others. Now, why are we interested in fire sprinkler systems? Due to fire safety. Fire hazards are everywhere. I mean, in office buildings, in residential premises, etc. And the fire protection systems have two important parts. One is called fire detection system, which consists of sensors and feedback loops to show the health of the building with respect to fire, and this is shown on a fire information panel. The other part of the fire protection systems are fire suppression systems, which are responsible to extinguish the fire in case of a fire outbreak. Fire sprinkler systems are an important class of fire suppression systems. Reliability is an important attribute of these fire protection systems, and reliability means what is the probability that given a fire outbreak occurs, the fire suppression system reacts to this fire outbreak by correctly performing its function. The other attribute of fire protection systems is efficacy, which means given the system has reacted correctly to the fire outbreak, how efficient is the system in terms of extinguishing the power. the fire outbreak. In this work, we are interested in the reliability of fire suppression systems, in particular fire sprinkler systems. And we compute the reliability using models that are static fault trees and dynamic fault trees. And we perform the analysis of these models using probabilistic model checking based approaches. So much for the introduction. Let's quickly look at the case study that we have considered. Here is the hydraulic system of our fire sprinkler system case study. And this hydraulic system is fed by two town mains, and the water is supplied in water is stored in two water tanks, and then diesel and fire pumps are used to provide this water to main sprinkler line of our sprinkler system, and then this line feeds water to different zones of the building. Now let's quickly look at the electrical system of our case study. Electrical system consists of three power sources, namely AC mains, diesel generator, and backup batteries. Automatic transfer switches are used to continuously provide the power to our main systems, which are sprinkler hydraulic system that I showed on previous slide, and fire indication panel, also called fire information panel, which is responsible to show the health of the building with respect to fire. Before moving further, let's recapitulate our objective. That is, we want to quantify the reliability of fire sprinkler systems. And our approach is that we model fire sprinkler systems using dynamic fault trees, and we contrast our dynamic fault tree models to existing static fault tree models, and we do so by experimentally comparing the reliability measures computed using DFTs and SFTs. Now let's look at some identified scenarios that we think are better modeled using dynamic fault trees. Here is a list of these scenarios. We identify several behaviors. For instance, we identify standby behaviors in fire sprinkler systems, and we think they can be better modeled using spare gates. Then we identified common cause failures, and we propose to model them using failure dependencies. We identified some monitoring mechanism failures, and we model them using priority AND gates, and so on. Let's look at a small example of standby behavior. In green box, we have static fault tree, and in red box, we have corresponding dynamic fault tree. The static fault tree is modeling a scenario where we have no power to drive our diesel pump. Actually, diesel pumps require a power source to provide an initial cranking to the pump. And this power source comes from the mains power, and if mains fails, then there is a backup battery system that is used to power to provide the power to drive system of the diesel pump. So in static fault trees, this situation is modeled using AND gate. However, we propose to model it using a spare gate, because we think that initially the batteries are in standby mode, and they only start depleting once mains power has failed. Therefore, the failure rate of batteries in their standby mode should be much lower as compared to their failure rate in their normal operating mode. So we propose to model our flat batteries using a standby type event. The next behavior is common cause failure, and underground water pipes corrosion and no water in towns mains are two common causes that can cause the event that there is no water from our town main. And we propose to model this situation using a failure dependency gate. And failure dependencies quite elegantly show in a dynamic fault tree the presence of common cause failures. Next, behavior is the monitoring mechanism, which is related to operator. And here in our static fault tree in green box, we have a situation where backup battery becomes flat and operator fails to observe this situation. And if these both events occur, then this lead to an event that the backup battery for diesel generator is flat. We propose to model this situation using a priority AND gate, because if operator observes the battery being flat, then he will somehow avoid the propagation of this flat battery towards the diesel generator. That's why we put the operator behavior as the first input of P AND gate. Here it is called monitoring problem, and the situation when battery is becoming flat in the second input of P AND gate, the right input. And if the monitoring problem occurs before the backup battery becoming flat, only then the backup battery becoming flat will be propagated towards the diesel generator. These were some of the scenarios. Now we quickly discussed some experimental results. The first result of our activity is a dynamic fault tree for fire sprinkler system. And this fault tree consists of 50 basic events. Then there are approximately 20 dynamic gates. We also report the failure rates both per demand and per hour for this dynamic fault tree, so that the researchers who want to use this fault tree can easily access the reliability data for the fault tree. Then there were several configurations for this system. For example, the first column of the table shows the presence or absence of basement tank and pump bypasses. Then the second column shows the various configurations for fire pumps, and the last three columns show three cases of considering a sprinkler head failure. Namely, case 1 says that two sprinkler head failures are considered as a failure of sprinkler head. Case 2 says that only one sprinkler head failure is considered as the failure of sprinkler heads. And case 3 says that one sprinkler failure or its surrounding 8 sprinkler failure is considered as the failure of sprinkler head. So in this work, we have considered only the first type of configuration, because the papers that we used to get the reliability data and the fault tree models, static fault tree models, only considered this configuration. Next, we show the size of our dynamic fault trees and the resulting probabilistic models. For instance, for DFT, we have approximately 7 million states and 23 million transitions. Next, we show the comparison of experimental results obtained through our experiments. The first column of this table shows different configurations as that is how the failure of how many sprinkler heads is considered as a failure of sprinkler head. The second column is taken from the table that is reported in the below mentioned paper. And the third and fourth column shows the results that are obtained through our experiments. And we can see that static fault tree and dynamic fault tree probabilities of failure on demand are quite similar. And in all of the cases, DFT computed probabilities are slightly less than SFT computed probabilities. The reason is that in our DFTs, we have a more realistic models. On the other hand, SFTs are a kind of over approximation of the scenario. And then the last column of this table complements our discussion on failure on demand that is given in the paper. Next, we also considered several measures of interest that go beyond the standard measure that is reliability. So these measures are summarized in this table. The first measure, that is the reliability, says that what is the probability that starting from state S, eventually within t time units, we reach a state labeled system fail. And if we complement this probability, it will give us the value of our reliability. Another property is full function availability, that says the probability of system within t time units not being in a system fail labeled state or degraded labeled state. We provide results for all these properties and also the details in the paper. Here we give a small part of that table. And in this table, we see that configuration 1 is slightly better than others with respect to unreliability and probability of failure per hour. However, if we talk about the full function availability, then the configuration 3 is slightly better than configuration 1. So much for the experimental results. To conclude this presentation, in this paper, we have modeled various scenarios of fire sprinkler systems using DFTs, and we have used probabilistic model checking to compute several properties of interest. And we observed that the increased expressive power of DFTs help in realistic modeling of the given scenario. All the results are available on the following link. And for future work, we plan to validate our models against real life fire sprinkler systems. That is, we need a collaboration with industry practitioners to see how the fire sprinkler systems actually what are their designs and what are their reliability parameters. And then we also want to synthesize the optimal configurations of fire sprinkler systems. That's all I had to say today. Thanks for your attention. Modeling.
Thank you, Saeed, for the talk. It's very interesting work. So, do you have questions from the audience? You can feel free and open your microphone to ask the question or write in the chat. In the meanwhile, I will ask you one question. So, in the work you illustrated very didactically way some combinations of parts of gates, to represent a fault behavior. So, is it possible, or is your intention to provide an automatic or a generic way to model the faults, or it is just adapted to the fire sprinklers system?
No, this is only adapted for fire sprinkler systems. However, we can generalize this approach to any system. But automating this, I don't think this is straightforward.
Okay, you don't think it's straightforward. I was wondering if you can choose it, for example, GATE and XR and use it to represent one kind of behavior, like a transient effect, or modeling a chain of events, of fault events that maybe would be a pattern that you can describe, a chain or a transient or a permanent effect, something like that. But you don't think that is straightforward?
No, that is actually a good idea, but you have to manually interpret the scenario that you want to capture through your DFT.
Okay, I understand. Also, you mentioned that you intend to validate your model against real-life sprinkler system, fire sprinkler systems. Do you have any ideas how to do that? It seems that it's difficult to compare, right? It's not a simple.
There I mean that if we have some collaboration with the industrial practitioners, maybe through discussions and through investigating the designs of their fire sprinkler systems, maybe there we can get some fruitful results.
Yeah, of course, they will be. Just another question, as you see, I like the patterns, the reuse of components and formula. So I remember in the past some very successful proposal of patterns for model checking. So there is a lab, Santos lab, if you're not wrong, that they provide standards of CTL and LTL formula. So you can represent absence, existence, response formula. You presented some queries, you call it like queries, model checking queries, that you use it to evaluate reliability, degradation, and so on. So these queries, they are a standard that someone could use, or you just elaborated those from scratch?
Some of them are standard. Like if you talk about the reliability and availability related properties, but some others, they are kind of goes beyond the standard queries. And there was some previous work from autonomous vehicles where they had this idea to give properties that go beyond the standard measures. So we adopted that idea and proposed some queries for the fire sprinkler systems performance.
All right. I really like the work. I think it's really interesting. So I don't know. Do we have any questions from the audience? That's the last call. We are running out of time, so I will just wait a few seconds if someone wants to ask the last question. Probably not. So I think to be in the schedule, we could end the session. I'd like to thank you again to the audience, and especially to the authors of the works. We had a really nice session this morning. I also would like to thank you the organization staff to help me conduct this session, and to the hard working on organizing LADC virtually, right? So thank you all. We'll finish now, and you can check the agenda in the website for the next sessions. Next we have a break, and that's all for this session. So